Welcome to this course that's about advanced computer architecture. And I am Ehad, and I am a faculty in electrical engineering and computer science. And my undergraduate degree was in control and computer engineering. And my doctoral degree was in computer engineering and science. So sort of I'll touch the electrical engineering, electronics, computer engineering, computer science, and then my research field is mostly in reconfigurable computer architectures and application-specific computer architectures and computer engineering in general, also electronic design automation tools to model and simulate those complex chips as well at the implementation level. So I myself quite excited in this field, which is evolving. We are going to see a taste of what's going on and what happened before, what's going on now, and what to anticipate in the future. The course catalog for this, in general sense, goes like that. In advanced computer architecture, including discussion of instruction set architecture, meaning that was the key in the history to make the programmers to be able to effectively use hardware to do anything they like to do, right? That was kind of the breakthrough. Before that, we had to design everything into the minute detail, no programmability. That wasn't easy. But the programmability changes the whole scenario. Sky becomes the limit now. So virtualization, meaning that multiple applications, multiple people can work on the same hardware domain. That's what it is all about. The memories, memory hierarchies, the cache memories, the pipelining, the vector processing, and a whole bunch of things like coprocessors or multiprocessor and architectures. That's quite a vast area. And multiprocessor architecture can go quite large. We will see those things and at large-scale computers. And of course, we want to be connected to the current reality. We don't want to be going away from that. That's why we are going to see a bunch of real processors. But to understand that things change daily, and we need to update those in our understanding. So the objective is to understand basics and principles. Those are the takeaway points, all right? So that we can analyze computer architecture, right? And when you say architecture, you can correlate with architects and civil engineers in the similar regards, and apply those insights and principles to future computers. All right. Let it be I'm gonna choose one computer over, or I'm gonna design it. In either ways, I need to know those basics. I need to know those fundamentals. Fundamentals of several things like principles, like roadmap. I need to know what it was before, what studied, what worked, what did not work. I need to know all of these things so that I know where I stand. So I don't want to try something that's tried already, that didn't work before. And I need to know the performances quantitatively. Again, bottom line is quantitative. We are talking about computers. It's not subjective most of the time. You can really boil things down to numbers. But sometimes the numbers alone, a single number is not going to tell us everything. So we need to use some graphs, some complex evaluation techniques we have to introduce. So the processes, the instructions, data path, pipelining, hazards that come with the pipelining, then we have to worry about that, right? So we are ambitious to add more hardware to it. We throw more hardware into stuff, then suddenly it brings up troubles that we have to fix it, right? So like, for example, one processor is good, two processors is better, well, fine. It brings up the synchronization issue. Then we have to solve it. And then we need to worry about, again, memories. Those are the fundamentals. First half of this course would be on like uniprocessor, how we can do it with the superscalar architectures, for example, or how we can do it with, instruction parallelization to some degree on a single CPU. We can call it as such at that point. But from now on, from the parallel systems, we prefer to keep it vague, processing elements, which could be very simple or could be very complicated. We love parallelization. Why? Because it improves performance. Instead of one doing one job, I can have two people doing it correct concurrently. Therefore, I can achieve a task faster, or I may meet my requirements faster. So instruction level parallelism, one way to deal with that at the very low end. Again, historically, this started like in early, maybe later 80s and up until mid 90s, and this worked quite well. So this is already done at the single processor level. The scheduling, to do things at the runtime, buy the hardware for us. And those are the things we are going to really look into, look deeper into that subject. And then why don't we work on the data level parallelism and like vector machines, SIMD, single instruction, multiple data. We're going to look into those acronyms. We're going to introduce GPUs. Here is another acronym. It's quite terminology rich. We are going to be specific on principles again, because those acronyms change as well. People may mean different things for the same stuff. So we have to be careful about what's going on. So the framework in this class is very important. So your goal would be to really have a good framework, frame and fill the gaps in the picture, then keep this alive, hang it on your wall. As the technology changes, then make a little change here, make a little color here, add another component, put another tree there, so on and so forth. So I think that's important to take away from this class. And like thread level parallelism, what's going on with the threads, multi-threads, why do I care about it? Is there a need, or it's just out of curiosity? Of course, there was a need, there was a demand for this, then I was able to do it, then I did it, sort of, multi-threading. And parallel systems, again, at a larger scale. I mean, we are talking about larger, like supercomputers. We are talking about massively parallel processors. And then nowadays, we have another domain of parallelization, request level. Zillions of people doing searches and watching movies, right? Or social media and data mining, cognitive sciences, autonomous cars. This brings up all these very exciting application domains and very exciting computers into our domain. And let's take a little brief. If computer architecture in general is kind of like a thick book, then consider this as first few pages. It started around mid-50s, and at the time we had, we needed fast computations, and this ENIAC computer was not based on transistors or nothing like that at the time, no chips, nothing, just the vacuum tubes that could be turned on and off. But at the time, computer architecture meant to be computer arithmetics. How do you really represent numbers and information and the text and ASCII and all these kind of fundamentals were being developed. And along the ways, the demand is growing for that, and then the technology is also improving little by little by little. And in 71, the first chip, monolithic chip, meaning that the bunch of things are manufactured at the same time on the same die, so that I can call this as my little simple processor. This was used in a calculator. In 2000 is a huge breakthrough. We have very complicated CPUs. But again, this is the first chapter. Then it evolves and it never stops. The reason I have this like hair cell and virus and all that, the transistors are so small. What does it mean? We have a lot of, it's a huge real estate, right? And computer architects are the ones who know how to put all these floor plans, like Lego parts. How do you really manage to design something very complicated to deal with some very, very complicated, designing of these computers. So again, welcome to Advanced Computer Architecture.